Alright, so I want to go into differentiation a little bit. We all know how to do it, but not all of us know exactly how it works. Obviously, we have here 5x cubed plus 2x plus 1. When you differentiate it, you bring the 3 down, and you reduce the power by 1. So you have 15x squared, 5 times 3. And you have 2 here, because you bring the 1 down, you reduce it to 0, this becomes 1, 2 times 1 is 2. And then plus 1 here, you have x to 0, you bring the 0 down, all of it becomes 0, so we don't have anything here. So I guess we can write plus 0. You can see, or we can just, cross it out. Right, so why does this work? I mean, what is differentiation in the first place? Well, let's say we have a curve, and the curve looks something like this, let's say. I'm not saying that this is the curve of 5x cubed. It's just an arbitrary curve. And let's say we want to evaluate it. Let me find a good point. I guess at this point, let's call this point 5, right? So if we plug the number 5 into here, and this was the curve that we're seeking to evaluate. So let's imagine that this curve is this, right? We plug 5 into this, we'll get some number, and that would be the gradient of this thing here, right? And that's what differentiation does. So why do we have this arbitrary rule where we bring the power down and reduce it by 1? Why does this work? These two things don't seem linked at all. Well, it's not just a magic trick. There is a method to the madness. So let's think about an easier equation. So let's consider y equals x squared, right? Obviously, here we have dy by dx is equal to 2x. Bring the power down, reduce it by 1. But why does this work? Well, let's think of x squared as geometrically. Let's think of it geometrically, hence as a square. So we have a square, and it has side length x. Well, then the area of the square is y, right? Because y equals x squared. The area is x squared, the area is y. So now differentiation is all about change. So let's think what happens as we change x. What happens to y as we change x? Well, let's change x by a little bit. Let's increase it by a little bit. Let's expand the square a little bit, like this. And on both sides, we will expand it by dx. And dx is a small number. It's very important that dx is a small number for this to work. Because, for example, let's look at this graph here. So we look at this point, and obviously we see that this is the gradient of the curve, right? Well, intuitively, yes, but how do we come to this? Well, you've got the point, but why don't we draw this line through? Like, why is that not the gradient? Well, how it works is you actually need at least 2 points on the curve. So this is your first point, and then you need a second point. And if we take a point that's farther away, like this one, then we get this sort of a gradient line, which is obviously wrong, right? We know that this is the correct line, and we're getting a line like this. So let's try bring it closer. And now when we bring it closer, it matches the line a bit more. So it tends to the line. We bring it like very, very close to it, we basically get the perfectly horizontal line. So it's the same thing here. As dx decreases, so i.e. the distance between these 2 points, anecdotally, as dx tends to 0, then we'll get a more accurate result. So if this area here is y, and if we've made this change dx, well, let's call the area of this whole thing here, let's call that dy. So then we can write, let's actually calculate the areas of all the strips separately. So obviously this length here is still x. So here we have x times dx, here we have dx squared, and here we have x dx as well. So then dy is equal to x dx plus x dx plus dx squared. Now, let's divide by dx on both sides. So we have dy by dx equals 2x dx plus dx squared over dx. So now, when we cancel this, and we cancel this, and we cancel the squared, we get that dy by dx is equal to 2x plus dx. Well, as dx tends to 0, this basically disappears. So we have our answer. dy by dx is equal to 2x. Right? So now, let us consider a bit of a harder equation. You might be thinking, well, okay, that's kind of cool, and we did get the answer that we were expecting, but it could be a coincidence, and it could. So let's consider y equals x cubed. Now, we have that dy by dx is equal to 3x squared, right? We know that. Now, instead of a square and its area, we'll be considering a cube and its volume. So, again, the cube will have side lengths of x, 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 and the volume will be y. So now, it's really hard to draw a 3D cube, especially with like the increasing lengths here. So your imagination will have to come into work here. So what did we do to the square? Let's think about it logically. We took this point and we basically stretched it out a bit, right? We take this point, we pinch it, and then we stretch it out by a bit, right? And we get this new side, we get this new side, and then we get this new square. So what happens here? We pinch this little corner of the cube, and what happens is we pull it towards us in this direction. And what happens is this face increases towards you, this one increases over to the right, and this one increases upwards. So when we do that, we get this new face here, which has a volume of x, x, and then a depth of dx. So we'll call it x squared dx. And then it's the same here. So we have x squared dx here, x squared dx here, and x squared dx here. So let's write it. We have x squared dx. We have 3 of them. So we'll write 3x squared dx. And you might be seeing where this is going already. But we also have to consider that when we do that, we also have these little cuboids that increase, right? So when we pinch it, we have a little cuboid that forms here, which has a face of dx by dx, and then it's very long. So it has a small face here, dx by dx, and then it goes down by x. So its area is x dx squared. And again, we have 1, 2, 3 of them. So we put the 3 in front. And finally, we have a little cube here that has a volume. I might have said area for this. I meant volume. If I say area, it's an error. I mean volume. And this little cube here that we increase, we will create, will have a volume of dx cubed. So now let's write out the same thing. So we have dy, and again, dy represents the volume of the whole thing that we just increased. So the volume is this plus this plus this, right? Because that's what the increase consists of. It consists of these 3 areas. So then dy is equal to 3x squared dx plus 3x dx squared plus dx cubed. So now, again, we want dy by dx, so we divide through by x, and we get dx divided by dx is just 0, is 1, not 0. So it just cancels, so we have 3x squared. And then here the 2 goes down to a 1, so we have 3x dx. And then this goes to a 2, so we have dx squared. And again, dx tends to 0, so this whole term is cancelled, this whole term is cancelled, and we have our answer, which is 3x squared. Obviously, I can't show you geometrically what happens at x to the 4 because we live in 3 dimensions. Space is in 3 dimensions, so, you know, there's no 4-dimensional cube that we can imagine. But this sort of concept is something that extends to everything. And I hope this video gave you a slight idea of where this rule comes from, because it's not just pulled out of thin air. There is logic behind it. Thank you for watching.